This is part 2 of the Python NumPy tutorial. We will start by introducing NumPy. NumPy is a core library for scientific computing. It is a core library because it stands as a dependency for many other scientific computing libraries. That's why it's a core library for scientific computing. It also provides a high performance multidimensional array object. So it's high performance because speed is what NumPy is designed for when working with arrays. And besides providing you this mechanism to create array objects, it also comes with a lot of tools for working with these arrays. These are methods and attributes of these array objects that you can use to compute array operations very fast. To use NumPy, all we have to do is start by importing the NumPy library. And let's talk about how NumPy sees arrays, or the arrays in the context of NumPy. NumPy sees that an array is a grid of values, and what's very important with NumPy is, unlike a Python list, in NumPy all variables and all values must be of the same type. They can either be int 8, int 32, float 32, etc., but they all have to be of the same type. And just like any other arrays, NumPy arrays are also indexed by a tuple of non-negative integers. The number of dimensions is known as the rank of the array. Unlike in regular programming languages where we have 1 and 2 dimensional arrays only, when working with machine learning development, you will very often have arrays of 4, 5, 6 dimensions as well. So the number of dimensions in the array is known as the rank of the array. For example, if there is an array of size 2, 3, 4 of these dimensions, then this has the rank of 3. The shape of an array is a tuple of integers. So we say that the shape of an array is a tuple of integers that gives the size along each dimension. For example, the shape of this array is 2, 3, and 4. We can also create initialized NumPy arrays from nested Python lists. Say, for example, here is a Python 2-dimensional array, and we can use this 2-dimensional array to initialize or create a NumPy array. And elements can be accessed using square brackets, just like in other in almost every other programming language and Python itself. A very important thing to understand is that Python arrays and NumPy arrays are two different things. They are two different objects. Python arrays, one example is that in Python arrays we can have, in Python lists, particularly in lists, we can have different kinds of objects, whereas NumPy always have same numerical data types. So say, for example, if we have a Python array or a Python object, the type method can be used to determine what type of variable it is. If I do type variable A, it will tell me if it is a string, if it is a array and list and so on. Now this type, when you do type of a NumPy array, all that it tells you is that it's a NumPy array. It doesn't tell you anything more than that. Whereas with NumPy arrays, the shape attribute always holds the dimensions of the NumPy array. So the shape attribute can only be used with NumPy arrays, and it can't be used with Python arrays. So let's just start by creating a NumPy array. Here's a Python list 1, 2, 3, and I can simply cast it to a NumPy array or create a NumPy array with this list. Now we have a NumPy array of rank 1 that has 1, 2, 3 in it. We can also print the type of A. In this case, it'll every time it will only tell me that it's a NumPy array, and a.shape, which is very helpful, tells me that it's an array of length 3. And I can also print individual elements of the list. Then if I try to replace or change specific elements within the list of a NumPy, I can try inserting numbers, and Python, sort of, since it only works with numbers, tries to interpret everything as number. So if I add a number, whether it's in double quote or single quote, it will try to read it as a number. But if I give it a string, then it's going to throw errors. So that's how we can create arrays. So we can also similarly create two-dimensional arrays. This is an array of rank 2, and we've converted it into a NumPy array, and then we can print it. Now, the attribute shape of a NumPy array is very, very handy. Say, for example, we load a text file into a NumPy array, let's say B, and we want to look at the number of rows and number of columns of this data. Then we can immediately use the shape attribute and check the shape of the data that we loaded. And for this reason, I like to call this shape as a hammer. It is like a tool that you can use to debug your code, fix your code, and like, you know, it helps you in your development. Just like other people use their tools for many other purposes. For a machine learning developer, these attributes like shape and methods like type serve you as your tools. NumPy also provides many functions to create arrays. That means you can initialize arrays with specific values in them. The np.zeros method can be used to create an array that has all zeros in it. np.1 can be used to create an array that has ones in it. So if I do, so right now the shape of B is, this is a really big array. So if I print it, it's going to take up a lot of screen space. So this is an array filled with all ones. We can also fill an array with a specific value. I can use the full method for that. I'm trying to create an array of size 2 by 2 and fill it all with 7. We can also create identity metrics using the I method. So it gives me an array of size 3 by 3 with diagonals all filled with 1. And if we simply want to create a random array, then random array of any size that we want, then we can use the np.random.random method. It gives you an array with values between 0 and 1. I can multiply it with 100 to give me a random array with values between 0 and 100. Next, we will look at various ways of indexing arrays in NumPy. NumPy offers several ways to index into arrays. The first one is slicing, and this is very similar to how we use slicing in Python lists. NumPy arrays can also be sliced. And since arrays can be multi-dimensional, unlike Python lists, we must specify the slice for each dimension of the array. Let's say we start with an example array. Let's say array matrix. Let's say we have an array that looks like this: 1, 2, 3, 4, all the way through 12. It is an array of shape 3, 4, and it has rank 2 because it has 2 dimensions, right? So here's how we can we will create that array 1, 2, 3 all the way through 12, 3 by 4 array. We can use slicing to pull out sub-array consisting of certain rows and certain columns. So here's the NumPy array. At first, in the first dimension, I specify that we go up to the second element. That is, we go up to 2 minus 1, which is 0 to 1. So the number of rows I'm selecting is 0 and 1. So I'm selecting the first row and the second row. And the number of columns I'm selecting is 1 through 2 because we don't go up to the last element. So that would be this column and then this column. So when we print B, it should print us this smaller set of 2, 3, 6, 7. So this is how slicing can be used. Something that's very important to keep in mind is this slice B of the original array. You can imagine that the whole thing is the original matrix and we're taking a slice out of that matrix. Its slice is a view into the same data. In other words, if you modify B after this, then A is going to be modified too. This is something very important to keep in mind. In other words, say for example, I set B00 as 77. In other words, I change the first element of this sub matrix B, subarray B to 77. Now, if I print the print the first row and second column of the original array A, I will get 77 too. I can print the entire element and entire array and see what it has, and you can see that it has 77 in the first or second column. So then this can sometimes be a problem because you may make slices of the original array and then make changes to it and accidentally make changes to the original array as well. So then how can we make a copy, not a reference, of an array? We can do this by using the np.copy method. So I can use c equals np.copy a, then now c becomes replicate entire copy of a, so that changing a doesn't change, changing c doesn't change a, and vice versa. We can also mix integer indexing with slice indexing, and however, if we do that, the rank of the resulting array becomes lower usually. Let's just start with an example. Say for example, we have an array like this of rank 2 and shape 3, 4. There are two ways in which we can access the middle row of the array, that is this row consisting of 5, 6, 7, 8. One technique is to mix integer indexing with slicing, but if we do that, we get an array of a lower rank, even though we may get the same content. Whereas if we only use slicing, then this results the smaller values, smaller shape, but the rank of the array remains as it was in the original array. Here's an example. So if I do A and give me the second row and all columns, one specified second row, all columns, it's going to give me the second row and all the columns, but now the resulting array is one-dimensional array. It's only rank 1. However, if I say give me all the rows from row number 1 through 2, although this is a single row, I'm asking it for a list of rows. So it gives me a list, and this list, which even though it only has one element, serves to obtain an array of rank 2. So this is a two-dimensional array with 5, 6, 7, 8 as the content, but even though it's a two-dimensional array, it only has one row and many columns, but with design, with the shape of the array is still two-dimensional. Similarly, I can ask to obtain the same two-dimensional array of rank 2 by keeping one as a list object. So if I ask for all the rows in this list, it's just like saying I'm asking you to give me a list of rows, but then my list only has one. So this also gives you a two-dimensional array. So if we print this, all of them will have the same content, 5, 6, 7, 8, but the first one gives you an array of one dimension, rank 1, and both of the two other techniques give you array of rank 2. So this we will need when if we want to, whether we want to obtain a subset of a matrix, or we want to later create a matrix of the same size as the original matrix, then we will use these two techniques differently. Either way, we can use something known as reshaping to reshape arrays into different formats as long as we have the same content. Same thing applies to accessing columns as well. So when I say col r1 equals a, give me all the rows and only those from column 1. So all the rows in column 1 will be 2, 6, 10. This gives you a vector, a one-dimensional array of rank 1. This gives all the rows and columns 1 through 2. So this will be the same column, but then now this gives me a two-dimensional array of rank 2. So it's the same content 2, 6, 10. This is a rank 1 array, and the same content 2, 6, 10, and this is the rank 2 array. When we index arrays using the technique of slicing, the resulting array is always a sub-array of the original array. In other words, the array that you get out of slicing is always a piece of the original array. In contrast, the technique of integer array indexing allows you to construct any arrays from the original input array. Let's take a look at an example. Say, for example, we have an array like this, which is a two-dimensional array, rank 2, and shape 3 rows and 2 columns. And say what we would like to do is select elements arbitrarily from position 0, 0 and 1, 1. From position 0, 0 and 1, 1. So say we want a smaller array that only has 1 and 4 in it. How do we do that? With integer indexing, we say this is the first index of the first element I want. So give me an element at row 0 and column 0. So you specify column in the second list. And also give me another element at row 1 and column 1. So this gives me 1, 4, the element as position 0, 0 and 1, 1. Now similarly, I can ask for 3 elements as well. I want an element at position 0, 0, 1, 1, and an element at position 2, 0. So then element at position 2, 0 would be 0, 1, 2, 0. So that would be 5. So this would return 1, 4, and 5. So in this way, I can select elements arbitrarily from any place in the array and construct an array that I want. Now this is very similar to saying, to manually giving the index to each individual element and saying, give me A00, A11, A20, make it a list, convert it to NumPy array and give it to me. So this is still going to give me 1, 4, 5. When using integer array indexing, we can reuse the same element. In other words, I can access the same element twice to create my list. So here I'm trying to I'm asking for an element at position 0, 1, and again I'm asking for another element at the same position at 0, 1. So this will give me the same element 2, which is at position 0, 1 2 times. So that's how you get the first 2, 2. The same thing I can specify by explicitly saying, give me an element at position 0, 1 and at position 0, 1. This would still give me a same NumPy list with values 2 and 2. Here's an example of the application of integer array indexing. Integer array indexing can be very helpful when selecting or even mutating one element from each row of a matrix. Say for example, so the problem is, say for example, we have an array like this, which looks like 1, 2, 3, 4, 5, 6 all the way through 12. And what we would like to do is select the first column element from the first row, third column element from the second row, first column element from the third row, and so on. So we can put this requirement, or we can say that what we want is we would like to specify the column number of the elements that we want. So in the first row we want column number 0, in the second row we want column number 2, in the third row we want column number 0, and in the last row we want column number 1. So what we have here is a NumPy array that specifies the columns at each row of the matrix. So with this as input, we can construct our integer indexing technique such that we subset or we select exactly the elements that we want. Now, to index the rows, we can use np.arrange. It is basically a method in NumPy that gives you numbers that start from 0 all the way to the number you specify -1. In other words, np.arrange 4 will give you 0, 1, 2, 3. So then we can specify the row indices first, and then the column indices, which is basically B, and this gives us a subset of this matrix where we are essentially selecting these numbers 1, 6, 7, and 11. And this is how this breaks down. So we are selecting a subset of matrix A, array A, with np.arrange4, which is essentially 0, 1, 2, 3, and the indices defined by b. So b is 0 to 0, 1. So then we are effectively saying, give me an element at position 0, 0, row 0 and column 0, A0, 0. Give me another element at row 1 and column 2. Give me another element at row 2 and column 0, and row 3 and column 1. So this is effectively saying I want A0, 0, A1, 2, A2, 0, and A3, 1, which is basically exactly what we were looking for. Now you may be thinking, why do we ever want to do such a complicated thing? One very common scenario is what may happen is as you are working with this, let's say matrix A, you may get these indices B from somewhere else. Let's say you did some calculations previously and then you determine the indices where you need to make the changes. So then you would have the indices in B, and then you can use this technique to either selectively change the contents of this matrix, which is basically mutation, or select these elements and then do something else with those outputs. We can extend this idea to mutate elements as well. So let's say, for example, for these selected indices, what we would like to do is add 10 to these elements, add 10 to 1, 6, 7, and 11. So this gives us all the correct indices. And we want to use these indices to update A and add 10 to these elements. So if we do this, it only adds 10 to these selected elements, 1, 6, 7, and 11. The next technique of array indexing is Boolean array indexing, and this array indexing also lets you pick out arbitrary elements of an array, and this is mostly used to select elements of an array that satisfy some condition. And here's an example. Say for example we have an array like this, 1, 2, 3, 4, 5, 6, a rank 2 array, and we want to select elements that are more than 2. In other words, here we are trying to select elements 3, 4, 5, 6. We can use this condition A more than 2 to select to obtain another Numpy array, which is basically of type Boolean, and it has the information about which index meets the criteria and which doesn't. So in this case, this prints false, false for the first 2 elements and true, true, true for the last 4 elements. Now we can use Boolean array indexing to construct a rank 1 array or to get the output of the array which meets the condition. So now since bool index has all the indices, I can supply that as input index to A and obtain a list from the original metrics that meet the criteria. And we can do all of this in a single concise statement by saying give me all the indices where A is more than 2, and use those indices to obtain a subset or a list from A. Like we discussed before, Numpy array is a grid of elements of the same type. So there are various data types that Numpy supports, but all of them are of number types. And one array can only contain elements of the same type. And Numpy provides a large set of numeric data types. So when we say data types, we are referring to the data types within Numpy, numeric data types that you can use to construct arrays. And when you construct arrays, Numpy tries to guess a data type when you create an array. And but there are also functions that we can use to force a certain type of data type. So say for example, if I create a Numpy array with 1, 2, it sort of automatically assumes that this is of type integer. On the other hand, if I try to create an array with say a floating point numbers like these, it automatically guesses the data type float 16 or float 32 and so on. And even when we are creating integer types, we can force the data type to be something specific. Let's look at the data types of these 3 Numpy arrays. So the first one is automatically chose as int 64, the second one to be float 64, and in the third one int 64. I can force it to see if I can make it int 32 and see if that works. Yeah, so it has now created an array with float int 32 type. basic mathematical functions such as addition, subtraction, etc. all operate element-wise on arrays, and I'll explain what that means. And these are available as both either operator overloads, that means we can use the existing plus sign, minus sign, etc., or as functions in the NumPy module. Say for example, I have two arrays x and y, both of type float 64, and I would like to do element-wise sum. What I mean by element-wise sum is we would like to add the first row, first column of the first array with the first row, first column of the second array. First row, second column of the first array with the first row and second column of the second array, and so on. So it's just each element in the first array gets added to the each element in the second array. So this can be achieved either by using the plus operator in Python or by using the NumPy function np.add. Similarly, Python supports subtraction, element-wise product, element-wise division, element-wise square root, and so on. Now, element-wise multiplication, just like the one that we saw using the asterisk sign, is not the calculation of dot product. It is element-wise multiplication. So the asterisk sign, it represents element-wise multiplication and not matrix multiplication or the dot product that we hear in mathematics. We use the dot operator, it's separate function, to compute the inner product of vectors, or to multiply a vector by a matrix, and to multiply matrices. And dot is available both as a function in NumPy module and as an instance of method of array objects. Let's take a look at the dot product. So dot product can be calculated using either np.dot or simply dot as a method of any array object. And this function returns the dot product of two arrays, and it behaves differently depending upon what you supply as input. If you supply two one-dimensional arrays as input, it computes something known as inner product of the vectors. And this is how inner product looks like. If we have two vectors, both one-dimensional, it multiplies element-wise and then sums them all together to obtain a scalar value. This is what happens when you use the dot product, the dot method, with one-dimensional arrays as input. For two-dimensional vectors, it is equivalent to matrix multiplication. And this is how matrix multiplication looks like. Say, for example, I have two matrices of size 2 by 2 and 2 by 2. Both are of rank 2 here. Then the standard matrix multiplication is you multiply the row of the first matrix with the column of the second matrix, sum them all together, and obtain the first element of your output matrix, right? And you repeat this for all other rows and columns. So if you provide 2D vectors, I mean, the dimension can be any, but if the rank is 2 of the input matrices, then it performs matrix multiplication. Now, if the matrix dimensions don't match for matrix multiplication, now if you remember, for matrix multiplication, the dimensions need to match. That is, the second dimension of the first matrix should be same as the first dimension of the second matrix. If that doesn't happen, and if that doesn't match, it does something known as matrix vector multiplication. And this is how matrix vector multiplication looks like. Here's the input matrix, and here's the vector that you are trying to multiply. It does the inner product type thing for each row in the input, each row in the first matrix with the vector in the second matrix, and computes the output. So the first row with the vector gives the first value, second row with the same vector gives the second value, and so on. For n-dimensional arrays, it is the sum over the last axis of A, the first matrix, and the second last axis of B. Now here are some examples. So say, for example, we have a matrix, a vector of 9 containing 9, 10, and another vector containing 11, 12. If I use the dot method, v dot w, then it computes the inner product of these vectors, because these are both one-dimensional vectors. And I can do that either using the dot product as NumPy method or as the attribute or as the method of one NumPy array. Similarly, say for example, I have V as the original array with a one-dimensional array, and I have X as a two-dimensional array, 1, 2, 3, 4. So now if I do X dot V, try to produce a dot product between X and V, this is the case of matrix vector multiplication. So it sees that the first array is 2D and the ranks don't match, right? So because this is 2 by 2 and 1 by 2, since the numbers don't match for matrix multiplication, it does matrix vector product and gives 2967, multiplying the first row with V and the second row with V and so on. If the numbers match for matrix multiplication, right now X is a two-dimensional array, and if I have another two-dimensional array, and now the ranks match for matrix multiplication, NumPy computes matrix product, which is basically the standard matrix multiplication. NumPy provides many useful functions for performing computations, and one of the most useful one is sum, and it serves as an example to understand how NumPy works as well. Say we have an array X, 1, 2, 3, 4, a two-dimensional array. If I print X, it's going to print the same content. If I do np.sum X, it computes the sum of all the elements and gives me a scalar value. If I want to sum along a specific axis, then I can provide the axis as another additional parameter to the sum function. Say for example, if I specify axis as 0, it computes the sum of each column and gives me the row sum. It gives me the total column sum. And similarly, if I specify axis as 1, it computes the sum of each row. So if we have this input matrix 1, 2, 3, 4, when we specify axis as 0, it looks for it tries to sum along axis 0, which becomes 4 and 6, and summing along axis equals 1 sums along computes the sum of each row, which gives 3 and 7. Similarly, to transpose a matrix, we simply use the .t attribute, and that gives you simply the transpose of the matrix. And NumPy arrays can also be reshaped using the reshape method. This is sometimes very tricky when you don't use it very carefully, but we can reshape arrays into various shapes. Say for example, I have a matrix that is a two-dimensional matrix, rank 2, 1, 2, 3, 4, and if I print the shape of this matrix, it will give me 2, 2. I can reshape it so that now it becomes a vector type matrix. It's still rank 2, but everything now flattened out into a single row. And if I print y, then I'm going to get the shape of 1, 4. So our original matrix was 1, 2, 3, 4, and we reshaped it to become a matrix of shape 1, 4. Now everything flattened into a single row. This is still a two-dimensional matrix, but now everything is flattened because we reshaped it that way. Let us look at the intuition behind broadcasting in NumPy. Broadcasting is a powerful mechanism, and it allows us to work with arrays of different shapes when performing operations. Say for example, one is a matrix of a different shape and the second matrix is of different shape. How can we use mathematical operations between these matrices? And the reason why we have broadcasting is because frequently what we have is a smaller array and a larger array, and what we usually want to do is use the smaller array multiple times to perform some operation on the larger array. And because this is so frequent, the approach or the technique of broadcasting works very well with NumPy. Say for example, we would like to add a constant vector to each row of a matrix. Say we have a matrix like this, 1, 2, 3 all the way through 12, and we have a vector that contains 1, 0, 1, and what we would like to do is add a v to x. So let's see how x and v look like here. So X is our original matrix, 1, 2, 3, all the way through 12, and here's our V. And we would like to add V to every row of this matrix. Here's a very naive way of doing this. We simply write a for loop that goes from 0 through 3, 0, 1, 2, 3. And for each value of this range I, we say Y, we create an empty array at first, Y, and we do yi equals xi plus v. So for each row in X, add V to it. I could also simply do, instead of not using X, simply do keep X here and update X and print X. So this gives me X with V added to it. So 1, 0, and 4, and so on. So this works. However, when X is very large, our bigger matrix is very large, computing this explicit for loop in Python can be very slow. Also, so that was the first approach, the naive approach. So we can think of this problem as saying that we are adding V to each row of our input X by sort of tiling, stacking multiple copies of V vertically. We can imagine this V to, like, we can make copies of 1, 0, 1, 4 times and stack them on top of each other and create another matrix and then add it to X. So this we can do using the NumPy function tile. So np.tilev gives us V tiled 4 times with the same shape as X by specifying for 1. So now we have V with the same shape as our input matrix X, and then if we can add it, then we have our new version of X. Right now we simply, since we had already updated X, it's giving us higher values. But this is another technique. By using tile, we can create a matrix and skip the our for loop, right? Now, what broadcasting allows us to do is perform this computation without actually creating copies of V, or without having to use the tile operation. And this is exactly what broadcasting is supposed to do. Say, for example, we have the same matrix X, and then we have our array V. We can simply add X to V. We can simply add V to X, and NumPy automatically does this for us. It understands that X is big, V is small, the vector length of V matches the row length of X, and it automatically tiles V and adds to X, giving us what we want. So this is X and this is Y. It automatically tiles it and adds element-wise with X to give us what we want. The term broadcasting describes how NumPy treats arrays with different shapes during arithmetic operation. So what does broadcast, the word broadcast, exactly mean? It means that a smaller array is broadcasted across a larger array so that they have compatible shapes. So it broadcasts the smaller array, makes it big enough to match the larger array so that they have compatible shapes, and then performs whatever operation we ask it to perform. And one very simple situation where broadcasting occurs is when we multiply an array with a scalar. Say, for example, we have a NumPy array 1, 2, 3 and a scalar 2.0, and we multiply them together. Intuitively, obviously, we think that 2 will be multiplied element-wise with every element in A. So the way NumPy does this, it sees that the second scalar is actually something that doesn't match the shape of the first array. So it broadcasts this into a shape that's same as A, and then multiplies them element-wise to obtain the result. Now, we can think of this operation as where scalar b is being stretched, or it's being extended during this operation into an array with the same shape as a, so that we can perform the multiplication. And the new assignments are b are simply copies of the original scalar. So we can think that now as b is stretched, it's simply making copies of itself to match the shape of a. Now it's important to understand this stretching analogy is only conceptual to understand. NumPy actually doesn't do this, and it doesn't do it in order to be memory efficient and computationally efficient. So it doesn't actually do it, but when understanding, we can think of that as what is happening under the woods for it to run. Now, broadcasting can become complicated when you have high-ranked arrays, not just a scalar and a two-dimensional array. When operating on two arrays and when broadcasting happens, NumPy first compares the shape element-wise. So when we say shape element-wise, we're not talking about the elements of the matrix, but the elements of the shape, the rank order, or the elements of the shape. And it starts with trailing dimensions and works its way forward. So if we have the first array as, let's say, the first array's shape is 1, 2, 3, and the second array's shape is 3, 3, it looks at the last dimensions, 3 and 3 of both the arrays, and it starts working its way forward. And broadcasting happens only when either the last two dimensions are equal or one of them is 1. If these conditions are not met, or if you are trying to add two matrices where the last two dimensions are not exactly same, or if one of the last two dimensions is not 1, then you will get a value error. Operands could not be broadcast together. This exception is thrown, indicating that the arrays are incompatible for broadcasting. Now here's the rule for broadcasting, to obtain the output of broadcasting. The output of broadcasting is the resulting array is the maximum size along each dimension of the input array. So we will look at concrete examples, but the output will be maximum along each dimension. Whichever matrix is bigger, whichever array is bigger, sort of takes over the output. Now also, arrays do not need to have the same number of dimensions. For example, if you have a 256 by 256 by 3 array of RGB values, let's say you have an image that is 256 by 256, and it has 3 channels in it, and what you want to do is scale each color in the image by a different value. And then you can say, for example, here's the input image that you have, 256 by 256, and if you split out the channels, the red, green, and blue channels, then this is how the image looks like. Now this is an input volume, an input image of array of shape 256 by 256 by 3. And what we want to do is multiply the red channel by 3, multiply the green channel by 15, and the blue channel by 30. So now this is a multiplication where we are trying to multiply an array of shape 256, 256, 3 with an array of shape only 3. And now broadcasting is possible here because the last dimensions match with each other. And when either of the dimensions are compared is 1, so unlike this example where we have the last dimensions as exactly same, if one of them is 1, then the other is used. In other words, in this case, if we had 1 here, then the larger one would be used. The resulting dimension would be 256 by 256 by 3. In other words, dimensions with size 1 are stretched or copied to match the other, and here the scaling vector can be thought of as having dimensions 1 by 1 by 3. So in this particular example, we can think of this scalar as having the dimensions of 1 by 1 by 3. Going back to the previous example, if we instead had this vector as, let's say, this was 256 by 256 by 1, and this was a 3 size vector, they are compatible because one of the last dimensions is 1, but then the resulting matrix would be 256 by 256 by 3, because the larger array for each dimension, the larger one takes over for the output. Here are some examples of broadcasting. Say, for example, we have the first array as having dimensions 8, 1, 7, 6, 1, and the second array has dimensions 7, 1, and 5. These two are compatible because one of the last dimensions is only 1. So they are compatible. They either have to be equal or one of them has to be 1. And the resulting array of this operation will be 8 by, at this in this dimension, the larger one is 7 by 7, by over here the larger one is 6 by 6 by 5. Let's say we have another example. The first array is 5 by 4, second array is just a scalar, so then these are compatible because one of the last dimensions is 1, and the output matrix is 5 by 4, the larger of the two. Here's another example. Say, for example, we have a matrix of 5 by 4, another vector of size 4. These are compatible because they have same size. The output array will be 5 by 4. Another example where we have two matrices of where the last dimension is exactly same. The output will be 15 by bigger of these two, 3 by 5. One more example where the last dimensions are exactly same. Once again, the output will be 15, larger of these two, which is still 3, and then by 5. Here's one more example. If you have the first matrix as like this with the last dimension as 5, another matrix with last dimension as 1, then bigger of these two, 5 is 5, these two is 5, so the resulting matrix will be of dimension 15 by 3 by 5. Here are some examples of shapes that do not broadcast. Say we have the first array as a vector of size 3 and the second array as a vector of size 4. Since the last trailing dimensions do not match, they are not either same, they are not, neither one of them is 1, so these cannot be broadcasted. Here's another example, and actually the most important example of all. Say, for example, we have the first array of shape 2, 1 and the second array of 8, 4, 3. The last two dimensions match because one of them is 1, but the second last dimensions do not match because neither of them is 1, and also they are not same, so these cannot be broadcasted together. Here's an example. Say, for example, we have a vector of length x and another vector of length 4 and length 5. So if we have these vectors and if I try to broadcast them together, we will get operands could not be broadcasted error because the trailing dimensions do not match. Similarly, say, for example, what we have is the first array of the first array that we have is of shape 4, 1. What we did was we took x that we had earlier, the first array of length 4, vector of length 4, and we reshaped it into a 4 by 1 matrix, a two-dimensional matrix. And we also have y, which is currently length 5 vector. In other words, now the shape of these two are 4, 1 and 1, 5. So now we would like to broadcast them and add them together. So let's see, the shape of the first matrix is 4, 1 and this is 5, so the trailing dimensions do match because one of them is 5, and the output matrix will be 4 by 5. Yes. Something interesting that you can do with broadcasting is compute something known as outer product. And broadcasting provides a very convenient way of doing this, that is calculating outer product or any other outer operation, outer sum or any other things like that. And here's an example of how broadcasting can be used to do outer product calculation. So say you have two arrays, A and B. These are two vectors essentially. One of them is of length 4 and the other is of length 3. So that's what we get. So if we try to multiply them, these are incompatible for broadcasting, so obviously you'll get an error. But to compute outer product, what we would like to do is multiply A and B element wise and get the resulting output as something like a 4×3 matrix. In other words, what we would like to do is, if this is A and if this is B, we would like to compute the multiplication between 0, 1, 0, 2, 0, 3, 1, 0, 1, 10, 1, 20, 1, 30, and so on. So every possible pairwise multiplication between A and B. So to do this, we can simply reshape one of these matrices, let's say B, into a different dimension, or sort of transpose it in a different way, so that originally A and B look like this, and now after reshaping, A stayed same, but then B is transformed into a transposed version of itself. So then with this, the dimensions of A is 4, and the dimensions of B now becomes 3, 1. That makes them compatible for multiplication or broadcasting. And then once you do that, we get a matrix where we can compute the product between the two vectors, and the output is essentially an outer product of these two numbers. And there's you can search online what functions are supported broadcasting and functions that do not support broadcasting. And these functions that support broadcasting are known as universal function, and you can search the list online.